Okay. So as introduced, my name is Kyra Campbell, and I'm at the University of Sheffield, and I'm very pleased to be here and to be talking about a really unglamorous topic, which is corrosion. So it's funny because I started studying corrosion as a postdoc in post-combustion CO2 capture systems, and sort of on a volley, thinking to myself, well, this is quite amusing and it does all sorts of weird and wonderful things. And somehow it's continued to trickle along, but the reality is actually the issues that are, the corrosion issues are quite complex. And moreover, the other thing you've got is that the hazards and safety risks are quite high. So one of the things that's quite interesting is that what I'm going to talk about today is sort of a piece of where we've been working on recently, but it is a small piece of a much bigger puzzle that's been going on in my research group. And so I think giving a little bit of perspective for that can be quite useful. So you have a sense of where this piece fits. So I have to admit that I also work on oil and gas systems for a wide range of reasons, including from a hazards and safety point of view, but also from the point of view of understanding that the CO2 corrosion comes in lots of different shapes and forms. And in fact, we're going to be faced with these challenges as we start to talk about CO2 transport. And so the knowledge we're gaining through systems that might be currently of interest actually will be deployable in the future for future problems. So what's interesting is that while we work on that, we've got lots of synergy with systems that are based on CO2 capture and transport. And given the landscape and the reality, it's actually quite important for us to look across the aisle, if you will, and benefit from that knowledge, irrespective of the fact that we're here as a community pushing towards those net zero goals. We actually can draw on that information. And so while today I am going to specifically speak about the corrosion that comes in an aqueous amine system, I'm also going to sort of highlight the fact that the approach we're taking is one that we can think about in terms of delivering on future challenges. Because in a lot of ways, this is just a proof of concept or an illustration or an anecdote, however you want to think about it, of a way in which we can address these problems that are going to keep coming about, because we're going to continuously be faced by new corrosion challenges, despite the fact that everyone thinks it's like the old guy, sitting in the room who knows all the information. Those old guys aren't working there anymore, and we've got better ways of dealing with it. Okay, so if I dive in now, what you can see here is an illustration about the carbon damage that you're going to see from a 5 molar MEA solution loaded with CO2. And I think you can make the comment that we would use stainless steel. Of course, we would hope to use it because the capital costs, even though the capital costs are higher, it's more resilient. I can have a whole conversation with you about that. But if we talk about stainless steel, which is a reality in parts of plant infrastructure as well as transport, we need to be braced for this scenario. And so one of the things we can see is that over the course of 10 weeks, we can see increasing amounts of damage. And understanding that damage profile from a chemical and a materials point of view is extremely useful in terms of addressing and establishing whether or not we've got approaches which can be used so that we could keep this type of infrastructure material safe, which costs on the order of 25% of a stainless steel, maybe even less. So what happens during this process from a point of view? So what we've got a mixture of two different forms of ferrite and cementite. And so the more labile iron from the ferrite becomes available. And so we're starting to see that that's the part being oxidized away. And you can already see in 1 week from an XRD scan on the left, which indicates the crystal structure, and we won't get into the penetration depth and things, but you can see that after 1 week, you start to see a little bit of change from the original structure. But as you hit 5 weeks, you can start to see an increasing presence of cementite. Cementite is indicated with the diamonds. I think they got lost, and the triangles are the ferrite. So we're seeing an increase in terms of the presence of that cementite, which indicates that the more labile iron ions have been removed from the surface. But in particular, that means that we're making changes to the microstructure of this solid, which means that its stability in terms of its ability to have the properties which somebody has purchased it for no longer exist. So let's talk a little bit about what's going on, because realistically, even if it looks ugly on the surface, sometimes we have scenarios where in fact that ugliness on the surface actually can have protective elements. And I think that you can find in some of our older research papers talking about that in depth. But realistically, we need to think a little bit about where those ions are going and what's happening to them, so we can understand in a system what we've got. So in the graph you see on the bottom left, you've got what is ICP data. So that's measured iron concentration in solution. So we're not talking about anything that's precipitated out. This is all dissolved iron content. And you can see in that very early yellow region, that's where we have that initial oxidation of the iron. And we've got that translation of iron to iron 2+ into the solution. And that's coming from that ferrite phase. We do have some solid precipitation, a very minor amount, and we can establish that that's an iron oxide of one of two types that we've got sort of depositing on other surfaces. Then as we continue in terms of weight, we see a decrease in the iron ions in solution. What's happening during that process is we're having an increase in the precipitation of iron oxide products. So obviously this is a point where we would see less iron in solution, an interesting point for us to consider in terms of the impact of that iron in solution on degradation pathways, etc. And you can see that we have a little bit of a shift in terms of a broader spectrum of types of iron oxide. Now, as we continue, what we see is that uptick back up again of the concentration coming and reaching some high levels, which we would expect would continue. So a few notes about that are really important is that could be coming from two sources. It could be continued oxidation from the surface of the iron of the sample, or it could be that there's reprecipitation of some of those products. We know a little bit more because we look at the mass of the collected precipitate, and you can see it's increasing, and you can see the damage to the surface. So I think it's relatively straightforward to agree at this point, right, that we understand what's happening over the course of time, and it's not good for our system. So with that knowledge, we can try to piece out what's happening. And I think this is where I like to blend the fundamental scientific approach with an industrial problem. Because the reality is that traditionally there are a range of inhibitors that you might apply in your system. You might apply them in solution, you might add a coating, but you do something to stop effectively that oxidation from happening. The problem is that that's not necessarily a well-informed decision in all cases, because we don't necessarily understand exactly the problem we're treating, and we don't really know if the treatment is actually appropriate. So what I do in my research group is we look at the underpinning science to make sure that the way we treat it is a way in which we can actually address the problem we have, rather than sort of just trying a whole bunch of inhibitors that we can find in the cupboard or standardly made by a company. So what you see here is some Zanes data. So Zanes is a synchrotron technique. We use the diamond light source as well as the electrosynchrotron in 3S to collect this data. And what you can see here, if you're not familiar with this type of data, is that you can see a set of standards which we've collected to understand a bit about the energy profile that they show. And so you can just look at this from a spectroscopic point of view in terms of thinking about the fact that the profiles need to match if you have the same thing. What you can immediately see is we've got our frozen solution, and then we've heated it to 40 and 80, and I'll get into that in just a second. But what's really interesting that you can see is that, first and foremost, it doesn't match particularly well. We've used a range of different fitting methods to understand our data. I've demonstrated one here. But what's sort of interesting is you can see that we kind of just have a combination of iron oxides and binding in the solution. But what's more interesting is that we can actually start picking apart our data and use heat to better understand what's happening in terms of the coordination of that iron in solution. And that's critical in terms of understanding how that iron is interacting with any of our species, because that may play significant impact in terms of the degradation sequence we would see. So I've circled here the pre-edge feature, which you can see, and then I've also noted our edge position. What's really useful for us to see is that we have probably mostly iron 2+ in solution, And additionally, we have an idea that its preferred structure is either a distorted tetrahedral iron complex or a diiron complex. And while right now, this is particularly sort of, I think one would call this, well, perhaps scientifically detailed information about what's happening in that solution, it lets us start to think about what is the nature of those complexations that we're having and how we can address that situation, either if we don't want it to happen or what types of molecules we might want to screen out because they encourage the degradation or decomposition of the solution. So it's sort of an information is power type of approach here. So if I go a little bit further, I also, I said I would point out the fact that we seeded the solution. So one of the interesting things in thinking about this process is also whether or not that complex is affected by the cyclone. So in this particular case, given limitations of the system we were working with at the same time, we only heated it to 80 degrees. But what's quite interesting is that the heating to 80 degrees resulted in changes, particularly to our pre-edge feature, where we find another node at a little bit lower electron volts, as well as an increase in our white line intensity. So yes, those are kind of details about it, but actually this also implicates the fact that when you create that complex, which is clearly going to occur, as you cycle it through, we're actually going to have a change in the nature of that complex. So it's going to start to move towards an octahedral or a diiron iron C+ complex. So why does that matter? It's back to the same conceptual idea that if we know what we're making, we can start to get an idea of how we can address the problem we have. So in this particular example, you can just see, I've just illustrated it here again, just so you can sort of see how starkly different that 80 degrees C sample is. So if we take that all as a package and we say, okay, now we understand about our system a lot better. So we have a baseline, which is a lot of what we were doing now. In previous work, we've looked at a wide range of other inhibitors that have been investigated by researchers. And in our recent publication, we've summarized them to try to give people a sense of comparison. And one of the interesting things is that copper complexes, the addition of copper behaves in an interesting way. And so I've included this table here just to give you a bit of a sense, because no matter what data I give you, you can't see anything because there is nothing to show. So with an inhibitor loading of copper carbonate, we get effectively no corrosion, and you can see nearly perfect inhibition efficiency. So this is talking about, as you can see, 9/10 of a millimolar in a solution of 5 molar MES, and we still get fantastic results. Now, these are consistent with what's been seen in literature. And if I show you, you'll see from the ICP, we have no iron, we have copper, right? So all these things make sense, but they also don't make sense. And so the baseline that I just showed you is part of the reason we use that to try to understand what the copper is doing. And so we needed to understand what the iron is doing. And what's really interesting is that the addition of a copper carbonate into this type of solution shows no consistency with either the parent complex or with any of these other complexes which we would anticipate. So why does this matter? Because we've demonstrated that in the presence of copper carbonate, you appear to get no corrosion, but the mechanism and the chemistry behind it are entirely unknown. And so with this data, we've been able to establish that as we start to look at our copper carbonate in things like isobutylene, we can start to see similarities. And this has provided us a really important set of information, because as we unpick this spectrum, which you can see is quite complex, we can actually start to see that it looks like a quinolone amine complex, which is quite an appealing structure in terms of being aware of it. It's quite large. And so what we start to think about is the fact that, in fact, even with heating, we can still see this. And so what's happening in our system becomes something that we have to probe using electrochemistry and using quartz crystal microbalances. And so what you can see here is that the addition of copper carbonate, as I said, shifts our potential way up, and then there's very little change depending on the concentration. So it's clearly not strongly concentration driven in terms of the behavior. As we start to look at things like anodic polarization, and I know not everyone will be familiar with these particular techniques, but what you can see is that when there's no copper, which is on the graph on your left, And when there is the addition of 2.3 millimolar of copper carbonate on the right, you can see that the graphs are different. And so you'll have to trust me in believing that this shift indicates that we no longer have active dissolution of our metal. And you can see that that's been flattened out, which means we've got passivation. So this is one of the indicators that that's what we have going on. We also use electrochemical impedance spectroscopy, again, which allowed us to use appropriate fitting to see that the charge transfer resistance is, once we add the copper carbonate, is increasing. So what all of these pieces of the picture are adding up to, along with our results from quartz crystal microballasts, where there was no deposition of any copper species, as well as with the lithoscopy, is that that copper quinolone amine structure is likely near the surface and is contributing to the charge transfer resistance, thereby reducing the ability of the iron to oxidize from the surface, but it's actually not adhered. So what I hope that I've demonstrated to you is that we can use fundamental science to understand a somewhat dull, but incredibly important topic of corrosion, to allow us to then find corrosion inhibitors which have the potential to address challenges. And so, as I said, this is one little piece of the bigger puzzle. But what you can start to see is that as we have to tackle these challenges within the area of CO2 capture, transport, and storage, we can think about it from this perspective to address and tackle the problem. I'd like to thank the following people who've been involved over the years, as well as the following funding bodies, and I haven't mentioned Diamonds or Electra, but I'd like to thank them as well for their support. Thank you very much. I appreciate your time and attention, and I'd be pleased to answer questions now or later.
Okay, any quick questions? Right. Thanks, Kyra, for how we can hold on. Yeah. Ready? Okay. Thank you for making it somehow cover level. But one quick question: how did you decide to go for copper carbonate?
So copper carbonate has been studied by other academics and literature. We've actually studied some others, but I want to just do an illustration with just one here, so you can see it. Copper also is quite relevant because obviously copper piping is used sometimes for transport, and obviously we have trace amines. So there's quite a bit of potential knowledge transfer to other systems where we might have trace amines. So it has sort of a dual applicability, but in this case, it's just for illustrative purposes. I've used this particular one. We can do others.
If I can make a quick interjection there. Very quick interjection. Flora used to say that when they taken back in good old days, the early 2000s, before aiming back to the old signature, they used to always say we've got a couple of places to vote in economy and actually fun. There's an excellent paper on corrosion development of soil where they talk about what they did to avoid corrosion and also the top corrosion.
Yeah.
Okay, I think if we find that we'll just move on. That's okay. Yeah, well, thank you very much. We have our last speaker. If you don't mind.
Yeah. Yeah, I tend to project, so I don't want to make it that. If I start thinking too loud. Here.
Yeah, the microphone.
Oh, okay.
Great, thanks.
Right, let's see if we can find my slide. Yeah, here we go. So I am Enrico Andreoli from Swansea University, and most likely the reason I'm here is because I received with great pleasure funding from the UKCCSRC for this project, a 3-month project. So compared to the large scale things that you have seen so far, this is a little bit more small scale, however, with quite a significant impact. Okay, so the title is this, so probably it's already putting you off because you see acronym. However, we focused on the scale-up of a metal organic framework. So a metal organic framework is a porous material, solid state, and what we are trying to achieve here is to develop, okay, a complementary technology to liquid-based amine to capture CO2. So this is solid state absorption. So I'm going to cover these three parts. The first one is to tell you what was the aim of the project and the motivation, the partners that were involved. Then later on, I attempt to go also in some chemistry, but I do it Lego style. So I show you a few pieces, try to give names. And the reason why I'm going to do that is because showing you how these materials behave tells you how important it is and how it can really make a change in terms of carbon capture. And finally, I covered some of the legacy of the project. So it was just 3 months long, but we achieved some nice results that brought to further development and current opportunities. So the aim was this. I told you the scale was smaller, so I talked about scale up. This is not million tons. We went from 200 milligrams of this compound, okay, to a scale of 100 grams. So it's a 500-fold scale up, and we use materials that are commercially available and very cheap equipment, as you will see. Those are all ingredients to make something so simple that nobody will tell you, I don't want to make millions of tons of it. It's just so simple to make, right? And the other one was with our industrial collaborator to estimate the cost, including CAPEX and OPEX on making this material. The motivation, as I said before, there you go, is connected to developing this alternative complementary method to absorb CO2 from a solvent-based system to a solid-state-based system. The reason is solid-state-based system should, in theory, right, at least promise to be more faster in the CO2 process, okay? The system is highly flexible. It should be energy efficient, environmentally safe. It will be emitting aim, for example, in the environment. And typically, the footprint of the actual plant is smaller compared to a different system. So these are the partners. At Swansea University, I was the PI of this small project. And Stephen on the left-hand side did all the work in the lab. Marco Taddei in the University of Pisa developed this MOP that I told you about, and then we show you some characteristics. And then work with us on the scale up. And in material, Cambridge-based, work with us to estimate the cost. So there you go. We go from very complex things to extremely simple things. There is a big beaker in the first picture, right? In this beaker, there is a solution of what is called the linker, okay? Tetrafluoroterephthalic acid, let's just call it linker, okay? And Stephen there is pouring into it a solution of the metal serum. So metal serum and organic framework, the tetrafluoroterephthalic acid. You just mix them in half an hour. So you take the yellow powder in the middle, and then you can also shape it, make granules instead of powder. It's really key when you have to use these materials on a large scale, and you will see you will use this material by swinging pressure, so you have gas moving very fast from one container to the other. You don't want to have powder, otherwise it goes all around the system. The price that the material helps us to calculate based on the characteristics under there, happy to have a chat with you later on, is about 16 pounds per kilo, which for a MOP is relatively cheap. In comparison, a zeolite 13X, which is one of the most used solid solvent materials in the world, is about 5 pounds per kilo, and synthetic carbon is around 7. So we're talking about 3 times cost of a commercial material. But still, you will see this material is quite interesting. I'm waiting for a response. There you go. So now to reiterate, just to attempt to save myself here, on the fact that we really did a scale up. We started from a test tube at 15 milliliters, it's something very, very, very small. So when you start very small, even if you do something not too large, it's scale up, right? And we started from a synthesis of less than 200 milligrams with the characteristics there. This one you saw in the left hand side, I don't want to, I would put you to sleep if I just talking about this, but it's an X-ray diffraction factor. What I would like you to do is try to memorize how it looks like. And on the right-hand side, it's an important part of the characteristic of this material is at different pressure of CO2, the material captures CO2. Okay, so the fact that this curve goes up shows that the material is able to absorb CO2. And it goes up to this value that is about 10% of its weight. So we ended up with a synthesis of 140 grams, okay, so from 200 milligrams. You might recall that the other one looks like this, so we are making exactly the same material, so we scaled up the right thing. And again, the absorption properties of this material are pretty much similar, just the capture dropped a bit, because when you scale up, some factors are not as good as in the small size. Okay. So this is just to tell you that, especially the UKCCSRC, we did what we were supposed to do. Okay. Now that's the part that either some of you will be engaged or some other will fall asleep, but I try, let's see if I can manage. So this is the smallest part of the moth you can take, and this repeats all around it to make the actual material. So these blue boxes, very technical, are the metal part. And those molecules that join all of them together in this framework are the linkers. Okay. And this metal oxide chain, okay, represents the metals and the oxygen that keep everything together. Okay. So now you see these chains all aligned nicely and connected to the linker, and the yellow spheres are the pores. So in this pore, the CO2 goes in, gets absorbed, and all the secret is there. We want that CO2 to stick on the material. So once the material is full of CO2, we just capture it in a pure form. So why do I bother you with this? For the next slide, which is even more than this one, but I'll try. Okay. This is work done by Marco today. So this is not part of the project, but it was very important for me to show you. So we have still the same linkers from blue, the same yellow, the same, metal chain. And now these are our linkers. They are different from before because there are some fluorine atoms around this equator. Okay. So what happens here is when you expose this to CO2, those bending rings do a sort of a dance. They all click at the same time, and you will see why it's so important. And what happens? Now this even works. These two metals here are the helium metals and oxygen in between. And you might see those linkers now pointing towards it, intensely with the fluorine. When the CO2 comes in, a tiny flip like that, so probably like 30 degrees, allows to attract a CO2 molecule that you can see in the temperature. What does this translate to? This concerted behavior of the linker allows to obtain a short-term curve of this kind, which has a step change in the middle. It's called a step change curve of absorption. So again, pressure of CO2 and how much CO2 gets stuck on the surface of the material. So why does this all make sense? And why would this material be a promising one for pressure swing absorption? The work in the solvent amines, when you want to recover CO2 absorbed inside the solvent, you need to swing the temperature. Instead, on this material, when you want to recover, so peel off the CO2 from the material, you need to swing the pressure. Okay. Here I have two curves showing the pressure of the CO2 and how much CO2 is captured. Okay. One is the standard isotherm, okay, also called Langmuir, for example, and one instead is this H-shaped isotherm. I want to show you why all these discussions so far. So we have two pressures now. One pressure of adsorption, the pressure I use to get the CO2 on the material, and a pressure of desorption, the pressure that I use to remove the CO2 from the material. Now, the working capacity of the material is between these two pressures. So from the amount of CO2 that I have on the surface as the absorption pressure, and the amount of CO2 that is left after I reduce the pressure. And the amount of CO2 recovered is Q1. You can see from this that if you have a jump like that, you can increase fundamentally the amount of CO2, the working capacity of the material. The material also has a very high selectivity, 2000. So for each molecule of nitrogen, you absorb 2000 molecules of CO2. And if we go back there, I do it quick. You can see if I operate at this pressure, at this temperature, which is 70 degrees C, okay, I can operate with a working capacity that is much higher than at another temperature, but much higher of any other standard sort of material. So the legacy, since this material is very promising, it doesn't cost much and you do it in a bucket, pretty much, okay? There's been a lot of effort later on to keep developing further the optimization of the scale up. And Dr. Enrico Garcia came from Aeroswap. Again, thank you for the UKCCSRC, who funded this ECR collaboration fund. And you can see the mythical reactor here, the big beaker, where Enrico did further development. Now we have much better space-time yield. So we are very close to what would be a very commercially valuable material to make. Another one, a visiting student from IQS Barcelona worked on shaping this powder, and we can now do a very quick shaping in spheres with the narrow size range with pretty good mechanical properties. So we can actually pack it into a bed and start using it. This is the very first, one of the first, the last slide. So why am I showing this? Opportunity. Within this project, it's called RISE. So here I'm changing chapter, it's like starting chapter 2. We have developed and deployed a PSA unit. So the hardware, the pipe, the container, where you would throw in the material that I just talked about, and you would actually use it. So within this reducing industrial carbon emission web-funded project, we deployed in Rockwell, not far from here in Bridgend, so probably it's a half an hour drive. On their manufacturing side, this unit, you can see their manufacturing side is this very big building. The starter is this white here, and in comparison, just to give you an idea of the size of this unit and what the unit can do. This tiny gray line compared to the big start is the line that brings the exhaust to the piston unit. Okay. So, but still, it's a different start, right? Here's the PSA unit offloaded from the truck the day that it was transported. The reason is you cannot take a photo really when it's all assembled inside the container. So you see in this format. It's 4 bags, 32 liters, okay, each, plus 4 smaller bags to do testing of advanced materials. So materials that are very expensive today. And then there are tanks for light and heavy products. So the unit has 96 valves. Altogether, it costs £500,000 to make, right? And through all these valves and connectors, what you can do, you have a high flexibility on transferring gas from any bed to any of the other beds, which is the high flexibility you would look for in terms of process design and scheduling in PSA. It has a dedicated instrument. It's called a process mass spectrometer. The unit is really operating properly to measure concentration with CO2 and the SCADA system. So in conclusion, we have successfully made half a kilogram of this material. We have also estimated the cost, which is significantly low. And maybe I convinced you that this material has some nice characteristics that allow to operate in PSA very, very well. Now, we have made progress in shaping the material, And we are looking, manufacturers of MOF are looking for us, maybe here in North Fluttering Real, but and because they want to make 10 plus kilograms of production of this material. So we're talking to with either UK or international company interested in scaling up the material. And also we have this option on testing in the PSA unit. And if any of you make materials for carbon capture, we are looking for partners to use the PSA unit. We can test a small amount of material, like within 500 grams, is already enough. That's all from me. Thank you. Any questions? Yeah. Probably. Yeah.
Hello, thank you very much for a very good presentation. My name is Mike from Andreoli University, and I wanted to ask you two quick questions about what was scale up, but in terms of particle size, so from the powder to pellet. Because you showed two different, you showed a pellet in the beginning,
yeah,
and then you said that you had a digital shape.
Yeah.
So my big questions are: how did you go from the powder to pellet? And what was the sort of uptake if you have for instance?
All right. So you're welcome. We attempted various options. So you might remember I showed you a picture where there was a series. So there we attempted to do some monolithic synthesis where you make a very high concentration pre-concentrate of crystalline material. And then you try to cross-link this material with the further synthesis. Okay. So this is what is done in material. The company I told you are expert in making monoliths. So we attempted to do something on that direction. Those weren't working very well. Then we looked at options in terms of mechanical pressing. So a bit of a way that you would find the pharmaceutical industry where you take powder in presses. There was a lot of carbon capacity, top carbon capacity of 20-30% if we were using a binder, also like PDA. The last one I showed you, I'm not going to tell you because, sorry, that's something that we want to, but it's based on a wet method. But quite quick in making those spheres. So that you mentioned the size also. So it would be a couple, 2 or 3 millimeters each. And those are mechanically stable. So also because of the geometry, they tend not to lock in each other. So when we did test, it appeared to be the best solution. And those, I haven't talked yet with Herman. I didn't mention the name. So I don't know how much they cut yet.
Thank you very much, Enrico. I'm from Cornell University as well. So, a couple of quick questions. The cyclic capacity of the material, do you have, do you see some good cyclic capacity overall, or do you lose the capacity after a certain number of cycles?
I have no memory that it's in cycle capacity material yet. So we haven't done it. Probably a few cycles, but not hundreds of thousands. I'm not in the position to answer the question because we don't have the data. But that's a very important. You would wonder why would you invest on making tons of these if you don't know the cycle capacity? But surprisingly, we haven't done it yet. But yeah, what point taken?
Sure, thank you. The other question I had was the mechanical stability of the material. So the constant stress testing that you've done, if you have a figure, that we're pretty much trying to do the same, but not obviously this type of material, we're working with carbon. We
used a very rudimental method, to be honest, but it ended up in a previous paper and accepted by reviewers. So what we do, we take a big cylinder, like a 5-liter volume cylinder, and the poor Herman was dropping it sounds crazy, but, and reproducibly this, and then recovering what was left of the particles, see what was the weight loss, Another one was put it in a vial and then use a mixer. We didn't use any ASTM or ISO methods because we don't have that. However, it's a good indication of the mechanical stability, at least relatively among the different pellets that we made. But probably I should ask you, if you know better, you can teach me a method that I can use.
You know, but I'm pretty sure we have a little topic to talk about after this.
All right.
Very good, thank you.
You're welcome.
Can I just ask you very quickly?
Yes.
What about water? You have to dry the food.
Yes. The top container at Rockwool has a moisture removal unit and dust removal unit. We have been doing work with the Harris work on moisture absorption, and the material is not really completely safe from water. It still absorbs some water competitively with CO2, so you would remove the moisture before.
Yes, thank you for interesting material and the scale and going forward. Actually, this is the question related to not the material, but the process around it. You presented the pilot, which seems to be straightforward in the development process, but how you try to have a little bit more granular and no pun intended approach to the process development around this material.
Yeah, so I'm always honest. That unit has been deployed a month ago. So the material hasn't been up in that unit yet. We don't have enough to use in the system. However, based on, so I'm not really answering directly your question. I'm going around it, but it's probably better than nothing. When you saw that isotherm, right? If we work in a specific range of pressure where there is this jump, it's very likely there is a high level of confidence that material will perform better than standard material that have regular isotherm. So the answer is, no, we haven't really yet even started using the material in the system, so there is no optimization yet. That's why I called it an opportunity at the end rather than an output, because that's the opportunity that we see on testing the material. Is it good enough? Maybe.
I think we'll just keep on going a little bit longer. So questions for anybody, really.
I was from University. Not my area at all, but just wondering, do these be great? Or do these, if you store your moss for a while in a storage container, are they eaten? Do they degrade? What happens?
Eaten, you mean biodegradable? I don't think they are biodegradable. Obviously, they are subject to oxidation because there is the oxide itself, the big blue chain, is just oxidized, but the organic part will certainly degrade with time. The good aspect is if, since you don't have to swing the temperature, it would be more a mechanical degradation rather than thermal, for example. We haven't yet, we should check again. I don't have an answer yet, but we have some batches that we did a few months ago, and it's probably a good idea to check if they degraded and what their porosity are. But the answer is I don't know yet. Everything degraded.
Thank you.
I've got a question for Kyra. If I understood it right, you said that the copper-based complex was close to the surface, but not connected to it. Am I mean, how does it?
Yeah.
Or is it just it's everywhere in the solution, but it's close to the surface? It's not located.
Well, there's very low concentration, so it's not really practical to imagine the fact that you would have it dispersed everywhere. If you did, it would be very, very low concentration. But if it's forming that copper-2 complex, it's likely that if the iron has like negative charge, then the way you normally have an electric double layer, you're going to find these covered in along complexes near the surface. Exactly whether or not we have some sort of desorption behavior remains to be seen. So QCM is, so for anyone who doesn't know, it's basically a piezoelectric, which allows us to detect very, very minute sort of adsorption to the surface. Now, it has a sensitivity limit depending on what frequency you use and things like that. And within our sensitivity limit, we do not detect during the process any adsorption to the surface, either of an amorphous material or crystalline. So that's our best guess. We know when we remove it, there's nothing there. We can see that. And in situ electrometry is a bit harder to establish because you can see that there are things near the surface, but differentiate between very hard. So I think that there is still a really important question to be asked there, because what would happen with more flow, things like that. But from the point of view of understanding that that complex does preferentially do that, could be beneficial at least in some conditions for application or for design of an inhibitor, understanding that chemistry and then implementing that in an inhibitor that could do it enough to do no fixture effect. So it's using that information. Does that make sense?
Yeah, well, yeah.
Okay. You still do not like the answer?
Well, no. It's an honest answer. You don't really know.
Yeah, I like honesty.
Yeah. I know.
It's a work in progress.
Absolutely. And I also got a final question as well. Oh, if you don't know. So you said that all solvents are within 5%. I mean, this is aiming for benefit. I mean, does this mean that actually it's hopeless if you pick out a solvent, or that within the 5% you can still find an advantage in particular applications? How do you sort of follow on from this rather final statement that 5% is actually the thing?
Now, first, I'm a software engineer. I don't want to get into chemistry. You can create a lot of chemistry. I'm going to talk about finance. And anything chemistry have a more reactivity that is more fundamental. That you can add more cost to produce. You have to look at those things, how you balance your operating costs. You cannot tell me you don't have any calculation, you don't have any. And you tell me you make up with 0.1 kilogram per ton, it's very hard to achieve. You can make it flat, but I don't think it's achievable during the dynamic operation. Anything you can achieve is a very stable quantity, never move anywhere. Yes, but when you're doing people going, I know US is different, or we don't have any background. We don't have any best load at all. Every plan is subject to the load fall. So then you look at the point rate, and you have to do the math. How much do you want to spend on? That's the only I can answer. Otherwise, I will be in the top.
Okay, we wouldn't want that.
Yeah.
So unless there's any more burning questions, I think we'll have to stop and carry on the discussion over 3. So thanks, speakers, for a very interesting talk.